Now, the next thing we're going to talk about, it's honestly going to take me about 2 minutes to really go over it. Then we'll start practicing it later. But what we're going to do is make the transition from here to integrals. Here's what you need to know. It's what I've already told you, but I'll reiterate it. Oops. What we're going to talk about is the definite integral. These things before, the integrals you were doing were called indefinite. They had a plus c because you weren't quite sure about the area. It was an area function, but you didn't know what the area was. Now we're going to be able to find the area.
Still 4.3.
Wait for it. There we go. Here it is again. Last time I'll show it to you. Area. Right now you know area as this. You know area is that, right? On some interval, a to b. There's another interpretation for it. It's very, very similar to saying this. Remember how you calculated derivatives with limits? And then we found a pattern for derivatives? And you said, to heck with these limit things. This is easy. I like this, right? Derivatives are great because they don't deal with limits, which is in fact a fallacy because derivatives are all about limits. You just don't expressly calculate the limit. You understand? Same thing with an integral. An integral is all about limits, just like this. This is called a Riemann sum, or Riemann sum, however you pronounce his name incorrectly, that's what most people say. The Riemann sum is taking all those rectangles and adding them up together. That's why it's called a sum. It doesn't really matter where that point is. We typically use left, right, or midpoints, but it doesn't matter. It's an arbitrary point. What that says is that when I add up all these rectangles, I do basically the same thing going from a limit using a derivative using limits to a derivative using the shortcuts that we basically do. And that's what we can do here as well. We say, you know what? The notation here really meshes up very nicely. I've showed this to you one other time, but now I'll show you exactly what we're going to have on top of this. When you take a limit of a sum, you basically add an infinite number of rectangles. Adding an infinite number of rectangles is denoted with this. That's an integral. Adding an infinite number of rectangles based on some function in terms of x. Where does the c sub k go? We're not talking about a specific point. We're talking about any arbitrary point that goes throughout the entire span of your x's on an infinite number of sub-intervals. And it's based on whatever variable you're talking about, dx, the width of each rectangle. If the width of each rectangle goes to 0 because n goes to infinity, that becomes that idea of a limit, limiting the x width, that's 0. Remember with our derivative, we took the x distance and we made it 0? Do you remember that? And we're taking the distance between 2 points and making it 0. And that's what we're doing here, the same exact idea. Only now we're adding together a whole bunch of little bitty rectangles instead of finding slopes between 2 little teeny points. You get it? That's the idea. Now where's the a and the b come in? Here's where the a and b come in. On an interval a to b, on interval a to b. This says this, basically. Add up all the rectangles with the height of f of x that have a width of a very infinitesimally small value from your starting point A to your ending point of B. Can you already do integrals? Awesome. I'm going to show you probably next time and the time after that, how to deal with this. It's not hard. I think you'll really enjoy it. Okay, so we are still learning about something called the definite integral. And our idea was that we can basically do Well, the idea was we had a summation, right? We took a limit of it, that was the area. We also made that into this integral and said, well, what the integral stands for is basically a limit of a sum. It's adding up all the rectangles where the partitions are, actually, you know what, for that to work, I have to make the statement, I gotta qualify it a little bit. You know how we made equal partitions? Those don't have to be equal. You know how we made left endpoints and right endpoints and midpoints? They didn't have to be there. They could be any point within any type of partition that you wanted to make. Because as soon as you make the number of rectangles go to infinity, those all, no matter what the size, they all go close to 0. Does that make sense? Even though some are closer than others, doesn't matter, they're all going to 0 anyway. So it doesn't even matter if they were equal. We did that for the sake of making it easy on us. But this is what this means. It means adding up sum, all the little rectangles, no matter what their size is, as we go the number of rectangles to infinity. So basically this is a limit of a sum, and I told you where that comes from, that's like the delta x. So this is the same thing we had before, which was called net signed area. This is net signed area. So basically this is this. And this is what you've been doing your whole, like, a lot, right? Aren't you glad I started you at, like, whatever I started you at? You did it my way, right? The way I showed you? Hope so. I did it my way.
It was a lot of effort, not a lot of results.
Now, before I tell you how to actually compute these with very little problems, because you basically already know, I'm going to show you geometrically what this means, okay? I'll give you just 3 examples on what exactly we are doing here. So when we talk about geometrically what this represents, let's talk about the integral from 1 to 4 of 2 dx. Now, firstly, can you tell me what the bounds of this integration is?
1 to 4.
Okay, so the x should start at 1 and end at 4. That's where our area starts and stops. What's our function? Can you graph 2? What is it? Straight line. Very good. Straight line? Or straight line? So basically horizontal line is what you probably mean by that. And it's not this way, it's this way, yeah? So this is our 2, our y equals 2, or f of x equals 2. And we're going from 1 to 4. This, folks, is what this integral represents. It's this area right here. That's what that is. Now, for constants, that's pretty easy, right? It just says, oh, we have this horizontal line. We're going from one spot to another. Let's actually calculate the area geometrically. What's our base?
3.
Good. 1 to 4 gives you a 3. What's our height?
2.
So what's the area?
6.
Here's what I know right now. This integral is equal to 6 square units, whatever the units are. But it's an area. That's what this talks about. It says, look, you can even partition it. No matter what you do, you add up the areas of those rectangles, it's going to equal 6. You got me? That's what we're talking about. Let's talk about a couple more. Let's do this one. How about x plus 2? Could you graph x plus 2? Hope so. Hope so. Yeah. So x plus 2 says I'm going to start at 2. My slope is 1, so this is going to give me that line. And I'm going to go from -1 to 2. And this is the area that I would like to represent, is the area of this region. How do you find the area of that region? Could you do it? Geometrically, could you do it? How might you do it?
Split it up into triangles.
Probably a triangle and a rectangle is how I would do that. So maybe break this one off right here. You okay with that? Let's find the area. What's the area of this rectangle down here? How are you getting 3? So a base of 3, a height of 1. So the purple area is 3. Okay, very good. How about the area of this region? Let's do it in blue. What's the base of our triangle? What's the height?
2.
Sure. And we divide by 2. So the area is also. What's the total area? By the way, total area doesn't always equal 6, just so you know. Just so you know.
The area of
When in
everything
doubt.
is 6.
When you gotta just put 6.
No, we did something wrong here, folks.
So it's cord.
The height is not that.
3 times.
Sorry, it's not the scale, but we did something wrong. This is actually 4.
So 3 times 3.
What now?
3 times
3 times 3. Over 2. 9 halves. If we want to add those together, we'd get 9 halves plus 3 halves. It's going to be 15 halves. You okay with the 15 halves? Sorry about that one. Yeah, that is 3 times 3. 15 halves.
You're just proving that not all areas equal 6.
Yes, that's what I was doing. That's what I was doing. I knew something didn't add up right. But, my dot was not exactly in the right spot. How many people feel okay with our areas so far? So geometrically speaking, this is not so bad. Rectangle, rectangle with a triangle, as long as we calculate our height right, we can do that. Base times height over 2. What about something like this one? This is going to look nasty until you really think about what's going on. How about that one? What's it mean? What's it mean? What does an integral stand for?
The area under.
Area under.
You guys over here are asleep. Come on, integral, come on, integral. What's a definite integral? What are we doing here? Areas. That's what we're talking about. We're finding the area of whatever this function is, whatever that function is, whatever this function is. Now, I think Michael might have said it, but what is this function? Oh, it's not quite a circle.
It's a half of a circle.
It's a half circle. Is the top or the bottom? Negative would be the bottom. Ergo, this would be the, that's the top of the circle. A circle is plus and minus square root of radius minus, radius squared minus x squared. So this is the top half of a circle.
That's a radius of 1.
A radius of 1. Very good. Radius of 1. That, right there. You okay with this so far? You sure? So this right here is that. Hey, tell me someone on the left-hand side of the room, what are my bounds of integration? Where am I starting and where am I stopping? Read my integral. Read my integral. See, my integral doesn't always say start where my function starts and end where my function ends. This actually says start here and there, just like we did over here. Start here, end here. So basically, we have a quarter of a circle. We have a quarter of a circle with what type of a radius? How much is the radius here? Can you find the area of a circle? Area of a circle, what's the formula for area of a circle? Come on now. Pi r squared. What? Y times 1/4. This would be the whole circle. We're taking a fourth of it. So this is basically a quarter circle with a radius of 1. Which is interesting, right? Without even having to calculate these integrals, we're able to find some of those areas. We're able to do them. We didn't do anything about those integrals. But the idea is, what you're doing is finding areas. There's a geometrical approach to it. If you can do the basic geometry, you can do some of these integrals. Now, of course, do we always have basic geometry to do?
Yes.
You would like to hope so.
I was having my fingers crossed.
No, but if I give you something like x cubed, there's no basic geometry with that. Like the x squared, there's no basic geometry with that. So we do have to have a better way. And we had the Riemann sums, or those limits of summations. We did those. That was one way. What we're going to do now is think about maybe a better way to do that, a faster way to do that. There's no better way. It's the same way. It's just there's shortcuts about that. Just like how with derivatives I gave you limits first, and then I gave you a quick and dirty way to do it. Actually, quick and clean. It was kind of nice. Pretty cool. Do you feel okay with this area approach to begin with? Can you always do it? No. But you're going to practice some of this on your homework. Be able to break up a rectangle and a triangle, some circle ideas. Now, before we do go further, I have to give you some properties, things we can and can't do with these integrals. So properties. Number one property. Okay, think through this. Think about this. Yeah, exactly. What's the area? Remember, an integral is an area. An integral is an area. What's the area?
No.
There's one.
Why?
Because it's the same point.
What's the area under a single point?
There's
There's 0. The width would be 0. The height, it doesn't matter. 0 times anything is 0. So whenever your bound goes from one number to another, and it's the same number, that's going to be 0. No matter what the function is, that's 0. This is the area under a point, basically. Which is why that doesn't work. Okay, second property. This is kind of an interesting one. I get evil looks from people on this one. The interval's backwards. That's exactly right. Which means this in terms of integrals. If your integral is written backwards, like what I mean, the bounds are backwards. See how we start at b and go to a here? That would be like starting at 1 and going to 0. What that's basically saying is, if the integral is written backwards, it's talking about the area that's under the x-axis. This is this definition. It says that in order to get this written properly so that you can do the integral, this is negative a to b. Well, it's negative integral from a to b. And yeah, they really should.
It'd be a lot simpler.
But that's the definition.
We didn't even get that from you.
Do you feel okay with that so far? Now, typically, our integrals are given to us in this fashion, where we start smaller number, we end bigger number. So this, we don't use it a whole lot, but it is there for you. It's something we can do. You all right with that one? Okay. Okay, third property. Just like before, even with definite integrals, you can always pull a constant outside of your integral. So if we have c times f of x, where c is a constant, this is the same thing as c times that integral. Also, just like before, this also works with definite integrals. If you have any sort of functions in terms of x being added or subtracted, any functions whatsoever, you can split those things up by addition and subtraction. As long as you don't change your bounds of integration, basically just says, hey, integral from a to b of f of x plus g of x or f of x minus g of x, split it up. We've already done this several times with indefinite. I'm just telling you now this also works with definite integrals, which is what we're talking about here. Also, don't forget your dx. That's got to go with both of those integrals. Okay, by show of hands, how many people feel okay with the properties we've talked about so far? There's one more I got to give you. I just want to make sure you're okay on this as we are here. So area under a point, hey, it's got to be 0. This says basically, well, my integral's written backwards. It represents a function that's actually below the x-axis. We're just writing it backwards. So we can make it negative and reverse our bounds of integration. That's great. We can still pull constants outside of our integral. That's still appropriate. We can still separate integrals by addition and subtraction, not multiplication division unless we have that constant. But addition subtraction, absolutely, just like derivatives did. Now the last one is interesting, is just for definite integrals. This doesn't work for indefinite, and you're going to see why in a second. But here's what we'll say. Now I'll give it to you with the picture first and then write it out. Let's suppose that we had some function. So easy. And there's some number between a and b, basically like some number c. Would you agree that the total area of this figure from a to b is written like that, if this is f of x? Then this is the total area of that whole figure. Would you also agree that the area of this whole figure could be written as the area of this plus the area of this? That's also a true statement. It says, if you find some number c that's between your bounds of integration, then this is the same thing as a to c. And then from where to where? C to b. Very good. That's another way that you can split up an integral. Find the area of just piece by piece. You can do that as well. As long as this number is between a and b, and they match right up to it. So you start at, you end at c, and then you start right again at c. Also, I don't know if I'll call this a property, but I'll list it anyway. Yeah, you actually could do it in reverse. These are not one way. I'm not going to write it twice. You need to know that if this is the case, you could write one integral out of that, for sure, absolutely. That if you have integral from a to c and then c to b, and it's the same exact function, mashed together, that works just fine. Okay with that? All right. Now, last up. This one, it's kind of a common sense thought, but think about this. If f of x is greater than or equal to 0, what's that mean? In terms of a graph, what's that mean? Positive. That's above or below the x-axis. So if the function is always above the x-axis, the function's always above the x-axis for every x on a certain interval, that right there says x is an element of AB. It just says x is within that, okay? So if you're confused on the notation, it says for all x's that happen to be in my interval. In English, that's what it says. For all x's that happen to be or are an element of the interval. You okay with the notation on that? If this is true for everything, you mean you plug in any x and it's always positive, it's always above the x-axis, tell me something about the area under the curve on AB. It's got to be positive. That's what this says. If f of x is greater than or equal to 0 for all these x's, then the integral from a to b of f of x dx must also be positive or equal to 0. Does that make sense to you? Can you think through the logic on that, the critical thinking on that one? If your function's always up here, and you can actually take an area of it, then, well, the area is going to be positive because it's always above the x-axis. You don't have that net signed area, which this represents, that's actually below. You don't have anything that takes away from it. It's always above. You follow? Same thing as in reverse. I'll just state it out for you. If f of x is less than or equal to 0 for all x in a, b, then the integral from a to b of f of x dx is less than or equal to 0. So it's kind of same statement. Basically. Those are really all the 6 properties we have. Area could be 0 if the numbers are exactly the same. Our bounds are the same, it's area under the point, no problem. We can flip bounds of integration by making our integral negative. That's possible. We can pull out constants. We can separate by addition subtraction, definitely not multiplication. We can also break up an integral if it is to our benefit, or put one together if it's to our benefit, provided our functions are the same, and there's a number between there that we can split up. That's okay. Also, this is just kind of a statement, but it is truth. If the function's always above the x-axis, the area's going to be positive. If the function's always below the x-axis, the area's going to be negative. That's the idea. How many people feel okay with our properties just fine? Cool. Let's try one more geometrically, and then I will go on into how to actually calculate these definite integrals. Trust me, it's not hard. All right. If you know how to do indefinite integrals, you're almost set. Just one more thing. So last little example here. Let's use some of these properties and what we know about the area approach to these integrals and find the area of this thing. There we go. Now that looks kind of nasty. In fact, you probably wouldn't even be able to take the integral of that if you didn't think about the area here. Because when you look at that, you're thinking, well, substitution, can I even do that with a definite integral, first of all? Because we haven't talked about it. Is that even possible? Will be. But secondly, even if I did a substitution, the substitution doesn't really work out that well for us, at least not exactly. So that might not even work. So we have to kind of think about the geometry in this particular part of it. Using some of these properties, tell me something I could do. Definitely separate. Separate. So from 0 to 1 of 4 dx minus, tell me something else I could do on the second part of it. After I write this way, I'll write every step for you. Yeah, absolutely. I can pull that constant 2 out in front of my integral. You okay with that so far? Now, at this point, well, we've got some things we've talked about already today. Tell me, can you find that? Yeah, that's pretty easy, actually. That's going to be, and I'll draw it in a second, that's just going to be a horizontal line at 4 from 0 to 1. Find that area. This one, what is that? That's a half circle, and I'm going from 0 to 1. That's a, we've done that problem already today. So what this says is, four, 0 to 1. What this one says is a quarter of a circle. So basically what our integral comes down to, our area is, what's this whole area?
4.
Minus 2 times, don't forget the 2. This was pi over, what was it, pi over 4? we got this area minus 2 times this area. So 4 minus 2 times pi over 4. If we simplify just a little bit, area is 4 minus pi over 2. If you really want to find the common denominator and do that, I think you'd get 8 minus pi over 2 if you really want. It doesn't do you any good to do that, but you could if you want to. Do you feel okay with breaking these things up and using some geometry? So in this section, that's what you're going to do. I haven't taught you how to directly attack a definite integral yet. I'm going to do that right now. This is kind of a roundabout approach. We say, let's think about the geometry. Let's draw a picture of it. Let's use our geometrical approach to find area, and that's what this represents. Would you like to see how to hammer out a definite integral just right on?